Okay, welcome everybody. Great to have you all here. I'm Patrick McGinley. I'm one of the technical advisors here at MasterSeries. I'm a chartered structural engineer. I've got around 12 years experience in consultancies, various design consultancies across the UK and Ireland, and I've been working at MasterSeries for 2.5 years now. So today, what to expect, we're going to be having a look at concrete analysis and design in MasterSeries. We will be looking specifically at the setup, analysis and design of a concrete frame in MasterSeries with regards to shear design specifically. We've covered a lot of the other topics in the past, so I won't be building up the frame to save a bit of time. There are plenty of resources online and within the MasterSeries software to help you with that, and we'll get to look at the concrete design module at the end. You'll also be able to preview the latest updates, which incorporate different shear checks, viewing options, etc. that can be carried out on slabs in MasterSeries. We've got our moment and punching shears checks that are already used. We will explore how to conduct linear shear checks for transfer slabs and other critical slab elements as well. So this will tie in well with an upcoming technical note which covers punching shear checks and the difference between using the code method and FE method in MasterSeries. The code method and the FE method in MasterSeries, and if you don't know what that means, we'll cover that around the end of the webinar as well. So we'll integrate the frame as we go along. So this webinar, it's for anyone designing concrete frames with MasterSeries and even FE software in general. So structural engineers, designers, it'll help you understand some of the challenges of designing concrete slabs, especially when considering shear checks. And I will highlight some of the many publications and guidances we will reference as we go along. It also targets existing or potential users who are considering concrete design with MasterSeries and those who want to understand the steps for shear verification in FE software, especially for transfer slabs. So I'm going to pull open always like to reference the MasterSeries modules here, so to give you an idea of where we're at. So we will be working within MasterFrame mostly. MasterFrame is our general 3D space frame analysis software, and we will be looking at the FE elements, or Finite Elements software, which is an add-on integrated analysis module with MasterFrame. And then at the end, we will be looking at the FE and concrete design module for concrete slabs and walls. We'll be focusing on concrete slabs today, but just to give you an idea of the different modules available with MasterSeries and what we'll be looking at today. As I say, MasterFrame, it's included with the PowerPad suite and the Building Design suite as standard, as is the FE elements, although we've got a limited version with the PowerPad suite. And then the concrete slab module, it's an add-on for both the PowerPad suite and it's one of the bundles or concrete design bundles within the Building Design suite. So a useful table for navigating the different modules and options available within MasterSeries. So as I say, we won't be doing any modeling within MasterFrame as the frame's already set up. I would recommend using, we've done a recent workshop on MasterFrame for new users and how to set up a basic model. So I would recommend that if you want to get familiarized with the software. And then I'll take you through the FE module and the concrete slab design module. So I want to pull up some references here. So there's quite a few references. I will try and pull them up as we go along so that you know where I'm talking about. So we've got the Concrete Center publication, How to Design Reinforced Concrete Flat Slabs Using FE Analysis. We've got the latest IStructE publication on the design of transfer slabs. This is free and it's fairly useful for our topic today. So we'll be referencing this quite a bit. It's noted here to start as well. Let's see. So this guidance, non-compliance with this guidance does not necessarily lead to the conclusion that the design of an existing transfer slab is structurally inadequate or non-compliant. So it gives some guidance there for existing transfer slabs as well. So definitely worth having a read through that if you're designing transfer slabs. We will also use the MasterSeries manual. So I've got it in PDF format here, but you will be more familiar with it on our online. And we've got an unreleased MasterSeries technical note, which will be available to you guys fairly soon. And that covers the different methods of punch and shear checks within the software. So again, I've referenced design guidance there. I don't want you to be taking anything that I've done in this model as design guidance. I've pulled this together in the space of a few days for this webinar. As I say, the aforementioned sources are your best design references, and I'll try to leave a link to each of those if you can't access them whenever we post the session online later. So hopefully by the end of the session you will be able to have some tips for setting up FE surfaces in MasterSeries for different element types, learn a little bit about best meshing practices, looking at the analysis results and interpreting those, designing slabs with consideration for shear design, especially linear shear checks. So again, feel free to ask any questions, provide feedback on your experience in the chat box as well. As I say, this will be recorded and posted afterwards. So transfer slabs, what are they? I've modeled one here. So you can see 4 columns on the first floor, 2 on the ground floor there. Well, internal anyway. Those are slightly offset for example later. They are popular because they are able to transfer loads from planted columns above to supporting columns below without the need for transfer beams. They're common in ground floor slabs where architectural layouts favor fewer columns. So they're popular because they enable these column grid changes between floors and a lot of architectural freedom. Now, they can be fairly structurally inefficient, as they will require deeper slabs, therefore more reinforcement, therefore higher embodied carbon. And as I mentioned there was currently no industry guidance covering transfer slabs specifically, but the IStructE publication provides high-level guidance for engineers. So for engineers, there's also greater construction challenges. There's more design considerations, more complex load transfers, higher potential for disproportionate collapse. I'll show you some loading considerations in the software in a little bit. And then as well, you will have to think a little bit more about temporary works and how the building looks at different stages throughout its construction. We'll not talk about staged construction today, so we will talk about the FE analysis for transfer slab design. So obviously it's difficult to carry out with hand calcs. Transfer slab design is FE is great for transfer slab analysis and design. Because of that, it can deal with unusual layouts and load paths and openings. I think we've got a wee opening model in there as well. And then it allows for more complex shear assessments. We've also, we do have a long-term deflection and cracking analysis module as an extension to the FE analysis as well, which allows you to carry out different time-dependent stages of the slab design, but we're not going to cover that today as well. So as I say, we've got a simple 3-story building here. We're looking at the first floor transfer slab mainly. There's not many other details of this building are relevant for today's webinar. We've got shear wall, lateral stability provided by shear walls, but the primary objective for today is to look at our shear checks. So I'm going to look at the first floor here. So I'm going to go under frame view plan at level 1. So I want to look at our FE surface setup here at the minute. So just a quick reminder for FE surfaces. So if you're familiar with the module, you will recognize that this is a valid FE surface. Now, I'm going to take you through the dashboard here. Valid FE surfaces need to be bounded. We'll get confirmation from that in the model space by a blue panel, and then in the preview pane by a black bounded square or whatever shape it is. If there is any bricks in our boundary, it'll be highlighted with a red node, and we won't get our blue screen here. Openings, I'll go on to those. We do have an opening defined here for, let's see, frame views. I'm going to go to viewing groups, turn that on, and go 3D. So we're looking at our first floor here. So we do have an opening here. The guidance says that all openings within 6D or effective depth times 6 of a column location should be modelled. Even small openings that might be typically ignored, like pipes or ducts near a column, they're crucial, as openings adjacent to columns can have a significant effect on the shear flow through the slab, and hence the peak shear stress values obtained from the models. So Openings also that are close to the edge. So I don't know if I've got any here modeled to have any openings. No, but if you do have an opening close to an edge, you might want to, let's say our mesh, we'll talk about that in a little bit. It's to do with meshing. So I'm going to get into meshing in a little bit. Our edge support conditions for this here slab, they'll tie in with the shear walls. We can change those releases if we want. So we can highlight that we want release conditions on particular shear walls or slabs. So I think in this you can apply your releases through the shear wall or through the slab. So in this case, we've got a shear wall and we've got our releases defined and selected for that boundary condition. Now that's up to you as a designer whether you want to include those or not, but that is how you do it within the software. And I think even the IStructE guidance advises against that for transfer slabs, so you will need to consider that in your shear wall design. Next, we'll talk a little about material properties. So on this floor, we've got a 500 thick slab, and to use the FE Slab Designer, it is essential that you have got codified materials turned on. You can specify user-defined materials as well, but the Slab Designer can talk to the codified materials. So make sure those are turned on whenever you are designing within the FE Slab Designer. They are probably a little bit easier to use as well. Material factors can be applied to all serviceability load cases or selectively applied to specific load groups, and you might want to consider that for different stages of your construction. So we've also got attached beams. There's no attached beams within this slab, but you have the option there to assign attached beams, whether it's center, bottom, or on top of the slab, and that's easily done by just selecting those and then loading. So FE loading can be applied as area loads, point loads, line loads, patch loads, or perimeter loads. And in this, we've got live load, dead load, and I've actually shown you here an accidental load for the IStructE guide gives practical quotes the Practical Guide to Structural Robustness and Disproportionate Collapse in Buildings publication, and it outlines two options available for justifying that a transfer system is suitably robust. So you could consider the notional removal of a transferring element, or you can treat the transferring element, beam or slab, as a key element and design it to resist a specified accidental load. So the guidance says it's a 35 kilonewton meter squared load on a 6 by 6 meter perimeter patch load, and that should be done as a load pattern and checked throughout the slab to check the worst case conditions for that. So you can do that within MasterSeries as well as a patch load. I've got it under A1. You can add different zones for A2, A3 and check that patch load throughout the slab. Column placement. It's common practice for structural analysis models to represent an idealization of the actual physical structure, but for rule of thumbs for your column locations, you'll see them. I've got them shown here inbound. So for overall model considerations like foundation loads and stability, you can simplify and model columns on slab edges, but for detailed slab design and punch and shear checks, the location can be critical, so it's best to model these accurately, and that is what we've done here. So you'll be able to see the edge of the column ties up with the edge of the slab here. The cross-sectional area of the column will be considered in the mesh as long as we have the slab stiff regions turned on, and we'll get into meshing now. So our meshing settings can be set up within analysis and FE surface meshing and global meshing options, and you'll get a window set up here now. I've got these turned on. So the initial setup, a good starting point for elements is to not be greater than span over 10. So you can reference, I mentioned this publication earlier, so if we go to, for example, page 8 there. So definitive advice can't be given to the ideal size of the mesh size, but a good starting point for elements is to be not greater than span over 10 or 1 meter, whichever is the smallest, and that goes into detail as to why, including some tests they've done. So we've got a default initial mesh size of 0.5, and in this model, I think it was, I can't remember where that came from, but we can keep that on 0.5. The IStructE guidance tells us for mesh refinement to refine the meshes in areas with significant stress concentrations, such as around column heads, and we can use automatic mesh refinement functions if available with your software. So if I pull that up, page 13 we're on, so just to reference that, yeah, it gives us a little bit of guidance on FE mesh density for 2D elements, and we can do that within MasterSeries by telling it to mesh our columns and walls stiff regions in the slabs. The stiff regions can be specified to better model interaction of the column and slabs to reduce the mesh sizes local to the different elements. So the next option is mesh to members inside FE surfaces. So this option causes the mesh generation to incorporate the geometry of members internal to the FE boundary, such as beams. This is useful for allowing the management of control of meshes in different situations, and you can use it to keep your mesh more uniform if you need. I've included a couple of beams on the roof here, so we can go through a few different examples and generate our mesh and see how they look. So our FE mesh, our local intensities, is our next option. These local mesh will increase the number of mesh elements at selected nodes. So the mesh around column heads will need to be suitably refined because there are significant stress concentrations in the slab, especially around both planted and supporting columns. And this is guidance again from the IStructE. So pull that up as well, just so you can reference it there. So refinement of mesh around columns head. So as I say, that is the guidance within that. So the disadvantage is that there will be more nodes to consider within the analysis, and it gives guidance on the minimum number of elements between column faces and analysis sections. So for shear force assessment, there must be at least one full mesh between the column face and the analysis section used to extract shear force values. We generally would say maybe a minimum of 2 or 3 elements between the column and the control perimeter for your punching shear. And then in this example, we've got a mesh size of nodes. So we're saying that within a radius of influence, so 0.65 meter radius, we're going to reduce the mesh size down to 0.1. So if you remember, we had it at 0.5 throughout. So we can work out, there's a little bit of recommended minimum radius guidance here. So that's 3b minus a. So the larger mesh size minus a smaller mesh size. So whatever those may be, as I say, we've got 0.5, I think at a 0.25 at a time. So that's maybe why it's 0.65 there, but we can change the mesh size to be reduced. So what I'm gonna do is take out one of these columns on the roof just for comparison. So I'll deselect that one just so we can see what it looks like whenever we run our meshing. So the next option within our meshing is our local surface mesh option. So we can specify each surface to be as per the global settings that we have defined within our global meshing options. We can set them by default if they are not turned on. We can set them to be turned on for all internal members. We can say, again, override our global settings and say no, or else we can identify and select different elements for the mesh to be selected for. So by default, we're going to go with as global here for all of our slabs. I'll maybe play about again with the roof here. We've got 2 attached dummy beams, so they're not actually doing anything. We can create dummy beams to control our mesh. So if I have this set as selected and allow ourselves to select a beam that we've defined here. Again, I'll reiterate, these are dummy members. These won't actually have any, these won't contribute to the slab at all. They're not assigned as attached beams or anything. So they're purely just to control the meshing or show you guys how to control the meshing. And then we can go into our slab stiff regions. As I mentioned earlier, they amend the mesh layout. They account for the cross-sectional sizes of your walls and columns. So you can see your 3D sizes there, and for each of the different surfaces, again, you can set those up. And if we go into our roof again, let's see we'll play about with the roof again and say select the column and wall member. So we're going to say we're going to omit the shear walls on this face, and the other side as well. So we'll just say select only for this face, and then we can see how the mesh looks when we generate it. So we can generate our mesh by going into analysis and regenerate FE mesh. And you'll see it getting built up there. And you can see already the slab stiff regions there. We can see it. Those are, I think it's a 200 thick wall. And then we've got different sizes of columns there. So if I've got the mesh turned off, if I turn on my mesh, we can then see we've specified a stiff region on this shear wall. There's none on the other, so it's not taking account the thickness of those shear walls nor the columns. So in the columns, we have specified a reduced mesh size around the column heads apart from this one. So hopefully that gives you a bit of an idea on the slab stiff regions, the comparison between turned on, turned off, the local mesh intensities turned off and turned on, and then finally our attached beam. So we have an attached beam without the mesh to attached members on or off and on. So hopefully that makes sense. And our mesh is generated. We're not going to be looking at the roof design here at all, so it's fine to keep that. So we're going to look at our graphical analysis output here, and then we can start looking at our shear results. So if we go into graphical analysis results and do an analysis of our different, we haven't went to the we haven't applied any one loading or anything on this model, just dead and live, serviceability and ultimate. So we can see our line elements, and we can see this is by default our geometry, axial forces. We can look at the values on those. We can look at our deflected shape and check those out and make sure that everything looks okay. So we're going to be looking at the shell elements mostly today, and we've got a few options. We've got the contour diagrams. So those are the results from an FE analysis, and they're presented as contour plots of stresses and forces. So we can look at our forces there. We can look at our forces, maximum, minimum as well. Moments, shear forces, displacements. We've got wood and armor moments is there as well. Our displacements, X, Y, Z, rotations, and then reinforcement requirements based on our moments, and then spring support reactions, and then some stresses there as well. So we can go through those, and if we don't have access to our concrete slab and wall design, this will be very useful in analysing our results. And I'm going to do an example of checking our linear shear checks within here as well. So we can look at our first floor, and as I say, if we just do a standard check on our moment X, moment Y, X, Y, you'll be familiar with those. And then I'm going to look at FV max for maximum shear value. Now, if you did know your VRDC max, so the shear capacity of your slab, you'll be able to put that in as a value there, and then that'll identify the zones that you need to be looking for and designing. Obviously, we've got the FE slab designer to reference a bit later, but if you didn't, you can identify these regions. I haven't actually worked it out for the slab here, but you can see obviously around the two supporting columns and the planting columns, there obviously is some critical shear checks that need to be carried out. Okay, and the guidance as well within the IStructE, let's just pull that up. So it does cover that. So if we go on to our output on the assessment of transfer slabs, we can see it recommends exactly that. So it says the easiest way to check this in an FE model is to modify the 2D principal shear results so the shading threshold is set to the VRDC value, which I just showed. So I'll just highlight that there. So peak smoothing is an option here. You can apply peak smoothing if you don't have your slab stiff regions set up for your different columns and shear walls. You can apply peak smoothing, but it's not applicable here now because, as I say, we've got the slab and shear walls set up for stiff regions. The other part, which is better for looking at your linear shear checks, is the section diagrams on FE surfaces. So we'll go into these and we're going to be referencing our different columns there. So I'm going to try and change the view here to show our first floor. Right. Let's see, frame view, just go to plan at level 1. Okay, so we can see our supporting columns below and we can see our planted columns above. Now what we can do is create a section diagram for the planted and supported columns. So if I go in and say I want to add a new line section diagram between two nodes, I'm going to say this is node 55 and 54. So I'm going to start at the supporting column and end at the supported column. The guidance says that you can take an average. So let's just call it linear shear check. Starting at node 55, ending at node 54. Average strip, we're going to say 4D. So the effective depth of the slab is around 440. So what's that multiplied by 4? So it's around 1700, 1.7. And let's just see, make sure I've got the right. Let's just fix the nodes, apply. Okay, so I'll delete that one and go back to your linear shear check. 1.6, apply. Okay, we said 1.7, apply. Just make sure we're on the right. Okay, so this is a section profile of our shear on this surface and between our supported and planted column. Now we can lock those to those nodes. Our average strip is 1.7, so that is taken from the guidance. So if I pull up the design guidance on transfer slabs, we want to reference here. So we'll be looking at this in more detail in the design, but we're taking a line from the supporting column, the planted column, we're taking it 4D wide in total, which is our 1.7 meters that we specified here. And then we are going to check the shear at 1D from that face. So by taking these nodes, we've got our X and Y values here, our X and Z values. So if we look at our Z values, we're at 7 meters. So we're going 1D from the column face. So this column is not 0.2 meters. 1D is 440, so it's about 640 from that. So let's say X at the, let's see, 7.6, and then that's going to be about around 600 less, so it's going to be around 9.4. So if we apply that, then we can see what shear forces we should be designing our linear shear for. That is just using the analysis options within MasterSeries. As I say, if you don't have the Slab Designer, you will want to use that or be able to check that for your shear capacity. Do your design that way, but it'll be a lot easier if you do have a concrete slab design module to do that. So I mentioned 1D from the face of the column for the guidance in here. If you're doing punch and shear checks, that'll be 2D. This is a reduced 1D perimeter. And we'll talk about that a little bit more when we get into the design module as well. We can also do rectangular checks for, let me see, assign to node. If you want to check your peak shear forces there as well, planted column and then our supported column for a rectangular shape around that. That's for your ultimate case as well. Let's go into our design module. As I say, we can do the design of this within the concrete design module now as well. So we access that through the design menu and concrete slab design. So we're going to review the existing reinforcement on this slab. We're going to go to, well, we'll keep it that frame view for now. Go on to the top here, and then we can see our first floor reinforcement. Now, this is a summary of the reinforcement in both directions. We've got a few new features within the design module. We've got some new drawing options. So before, we just had our hogging and sagging moment capacities to check. We can now include for shear unity hogging X and Y and sagging X and Y as well. We can add linear shear checks within our strip reinforcement, and then within our punch and shear checks, we have some new settings now for closely spaced planted and supporting columns. So For this, we're trying to interpret the IStructE guidance. So if we go and we check the hogging on this, so we'll see that all our basic reinforcement, our peak reinforcement has been set up. So we've got peak reinforcement at all of our columns, and we've got larger zones with more reinforcement at the locations of our planted columns and supported columns here as well. We can review those for both directions, faces for our moment, and then I'm going to show you the new feature. This is our shear capacity and shear unity ratio contour outputs for both directions, X and Y, for both faces. So these are useful for identifying areas beyond normal punching shear where slab shear capacity may require a more detailed check, for example, our linear shear check. So this does exclude the zones we've set up for punching shear checks. Even though we see failures occurring, this is the unshear reinforced capacity where we need to do more detailed shear checks. So that'll identify the regions that we need to zone in on, so you get a clear indication from your contour plots there where we should focus our attention. So this shouldn't be used as an indication of final design failure, as no support face enhancement is considered, and it excludes the zones inside the U1 or 2D punching shear perimeters setup. So if we review our peak zones here, as I mentioned, we've got our planted columns and we've got our supporting columns there with reinforcement on the top. And then if we check our punching shear checks, we want to assign punching shear checks to all column and slab intersections. First thing we would recommend is that all your punching shear checks are set up to use the FE shear forces method. As I mentioned, we've got a good technical note on this that I pulled up earlier, and it'll give you a bit of background information on why you should use the FE shear forces option within MasterSeries, especially when you're dealing with these transfer slabs as well. I'll give you a brief summary here. I will check the supporting column 1. I'll use this as an example. Having the FE shear forces method turned on, it gets the shear forces directly from the perimeters that are defined within the FE analysis results. So you can see that visually there. You can see the peak principal shear force at the 2D perimeter, or U1 there. When using the FE results, the shear on the punching perimeter under consideration is calculated directly from the FE results, and the effect of the bending in the slab and column is automatically accounted for. So if I have a look here, we've got an average effective depth multiplier, which averages out this peak between whatever we specify it to. If I say it's 0, we can look at the calculation output and we can see that it's going to base the VED max VED1 on 230, but by default MasterSeries has that set at 2, so you can see that's down to 216 now, but the IStructE guidance recommends that it's averaged over 4D. So again, if I pull open the document, if we zoom in there, we can see that this is taking 4D, 4 times the effective depth for that perimeter to average out the forces there, and it gives a few different examples where you can see that. So that's the peak principal shear force at 2D perimeter of the supporting column, and that's averaged out as well, 2D either side of the peak, so 4D in total. That's basically what this force average depth multiplier does. We've got another new setting in there. We'll talk about that in a little bit as well. So when using the FE results, the design force area amends to include an input to define the width over which the shear forces are to be averaged. The averaging width is specified as a multiple of the slab effective depth with a default value of 2 times the effective depth. Now that's from the MasterSeries manual. This is the approach we've implemented and been recommending since we introduced the punching shear checks a few years ago. So if we want to interrogate those results a bit more, I'm going to do that because I want to compare it to the code method. So we'll look and we'll see that the shear force max, it's going to be 175 kilonewtons per meter. So our VED is going to be 0.386 newtons per millimeter squared, and VRDC max is 0.425. So what I'm going to do is switch over to the code method and compare them. So the code method relies on the assumption that the slab loading is predominantly uniform, and any variations in shear stress distribution are due to the eccentricity of this uniform loading relative to the column control perimeter. So the design force at the control perimeter is estimated by considering bending in the column. If we compare those results there, our VED using the FE is 0.386, and it is using the code method, it's a lot less, so it's 0.13. It also includes for a beta factor to estimate the peak concentration of shear forces at the 2D control perimeter when assessing punching shear in concrete slabs. So it's estimating that, whereas the FE method is pulling it out from the model. So the standard EC2 beta factor assessment method is not appropriate for transfer slabs. So as this approach relies on the design code's formulas and coefficients to determine the shear forces acting on the punching shear perimeters. The effect of the bending moments transferred to the column will be considered when determining the shear force and shear force distribution. So you'll see in there as well, we've got forces from the model, the columns being taken into account there in the code method, whereas, as I say, the FE shear forces are taking the forces directly from the model. So the FE shear forces method generally provides a more accurate representation of the shear forces, and the code method relies on simplified assumptions and code-based calculations. So the recommendation is to use the FE shear forces method. It's more preferable as it considers the behavior of the forces, ensuring that the FE model is set up correctly and the mesh is suitably refined to accurately capture the shear distribution around the column. So it's worth considering the limitations of each method and obviously apply engineering judgment when interpreting these results. And you can always validate these results by comparing them with hand calcs or other independent methods. So the other way to make sure that you are using the FE shear forces checks just quickly is visually. You can see the shear force diagram or the 2D control perimeter diagram showing up each time you click on one of those. So that's a summary of the FE and the code methods. So also for whenever we've got closely spaced, planted and supporting columns, we can override the perimeter multiple. So it's 2D by default whenever we've got a spacing greater than 4D. When it's less than 4D and above 2D, we can specify what that is. And in this case, when our columns are 3D apart, our column spacing face to face, we can take half that for the perimeter D multiple override. And so now I want to jump into our linear shear checks. So the actual design of the section diagrams that I pulled up earlier. So linear shear checks are now provided with strip reinforcement checks. So having assessed the shear unity ratio contours, this may inform areas where a linear shear check may be required. That was under the basic drawing. So these, once we've identified we need to apply linear shear checks, we can go on and create them within the strip reinforcement entry there. So you can provide a strip even without additional strip rebars, and then you can optionally turn on the shear checking for all points along the strip length, and it can also design your shear rebar required. So in this here model for our moment checks, we've covered all of those within the basic, between the basic and the peak reinforcement. So these strip checks are only going to be checking for shear reinforcement. And if we go into our guidance, let's see, page 29. Okay, so this is how the guidance has recommended that you specify your reinforcement or your shear bars for your linear shear checks. So you can recognize these punching shear reinforcement diagrams here, either side, but for the direct transfer zone, we're going to have shear lengths at maximum spacing of 0.75D in this direction, equidistant spacing longitudinally, again 0.75D, and then it's taken from, instead of the punching shear checking for 2D, this is checking for 1D. So you'll have an increased number of increased area required for your shear links there. I'm going to go through an example on this here. So we have them specified in here. I'll take you through this one first, and then we can replicate it again. So this is our linear shear check 1. Our supporting column is Y value or Z value 10, and our planted column is at Z value 7 there. Taking you through linear check 1, add or replace. So it adds the basic rebar. We're not actually specifying any rebar here, so it doesn't really matter. We can avoid confusion, take that out. So the bar orientation is parallel. Whenever we draw this in, we can also look at our section diagram. So earlier we looked at the shear, so we can change it to shear, and you'll recognize that diagram from the one similar to what we created within the FE analysis output results. So that is taking the maximum shear value at a distance 1D plus the column, half the column width, and giving us a peak force there of 410 kilonewtons. But so we're not specifying any bars there. Our design force average is over the full width. The full width is going to be 4D. So that is 2D is 0.9275. So specified geometry from the start to the end as the same. Specified the start at the supporting column and the end at the planted column. And I've turned on our shear check. So this is the new part of the linear or the strip reinforcement checker. So we can check our shear, yes. We can tell it where to start. So we're saying the support width plus 1D. So we can take it right to the start there at the node and say, or we can take it right to the node. We can say the support width and then specify the support width 200, or else we can say the support width plus 1D, and that automatically calculates the distance based on the support width you specify plus 1D from the calcs there. And then our support end, it's going to be we've got a thicker column there at the end, and then we can say that if we want to, we can provide shear reinforcement. So if I turn that shear reinforcement off, it's telling us that we've got a failure and we need to provide those. So we can specify what reinforcement or what shear reinforcement we want to specify there. And we've got 16s. I've used 16s there because if we go into the punching shear check, it's specifying 8 number 16mm bars per perimeter. So just taking the same size, we can then specify those. So as I mentioned earlier, you're going to have to detail this manually. So you're going to be taking your direct transfer zone, and that supersedes the reinforcement or the shear links on the side where the linear shear check is being carried out, because this is a more conservative design for 2 reasons. It is taking the shear force values at 1D from the face of the column instead of 2D as per your punching shear checks. And then it's saying that a maximum spacing of 0.75D in both directions as opposed to 1.5D from the punching shear checks from that. So you'll get a lot more reinforcement there. The software tells you what exactly you need. So you need 16mm diameter vertical legs at 335 millimeter transverse and longitudinal and transverse spacing of 335 millimeters. And then, as I say, we can compare that to what we're getting at 2D then from the column face, and just for a sanity check there as well. So that'll need to be detailed manually there, but if you are able to work your way through that and understand everything that the guidance is providing and what we're saying, you should have your linear shear checks done. Now, over on this face, we've moved the column in a bit, so we've reduced our distance down. So instead of being at over 4D, we've reduced it to within 4D, so it's actually at 3D, the spacing between column faces. And as I say, then that allows us to amend or override and then change our average to 3D and specify that D value to 1.5. Let's see. So, okay, Martin O'Gara is here. Now, this is not available for users yet. It'll be in a release, and I'm sure it's going to be in the coming days. But Martin O'Gara is here. Martin is the lead developer. So maybe Martin wants to jump in and say a few words. We're going to be taking questions as well here on this. So I'm going to have a wee look at what questions have been asked throughout the webinar here. We're going to have a wee look and answer some of them. So hopefully that all made sense. As I say, if you've any questions on it, do shout. Let us know. It's 2 o'clock now, so let's have a look.
Everyone, and thank you, Patrick, for taking us through that quite technical content. We're just reviewing those questions that have came through now, of which there were many, and happy to participate and jump in with some of them. A lot of people requesting the materials that we're using today and sharing links with those. Obviously, some of those are proprietary documents, some of them are free. We'll share links where you can purchase any documents, for example, from the Concrete Centre, or any resources where you can download the free content, and obviously the links to our MasterSeries free resources for your US customers with regards to the technical notes and the manual documentation. Okay, we had a question there with regards to how we handle drops. There is an input option in the punching shear. It's not part of the modelling. It is something that is considered post-analysis as part of the design phase. And in the geometry, one can input a drop thickness and a drop projection as an equidistant, and then that follows the rules of the code with regards to doing multiple punching shear perimeters, both within the drop and outside the drop, where that's necessary to do so. So that's something then that's done there. You can see then you're getting a few perimeters involved then, and the most critical perimeter then is used for the design purposes. Okay, just a few more questions there with regards to the linear beam shear zone. Patrick, maybe if you could go along to one of those strips there and have a look at that. And perhaps just turn off, Patrick, the contour drawing for the shear unity ratio and just take that back to none. And let's just visit, let me see now. Yeah, let's just take off the meshing there as well. One of the new things actually we have, and this partly answers this question here with regards to the new shear checks that have been added to the strip zones. Strip zones previously were only a means by which to add additional one-directional reinforcement bars to one side of the slab, either the top side or the bottom side. Now, you can use these strips without, maybe Patrick referenced this, you don't necessarily need to associate additional bars with the strip. You can provide the strip as is on top of the basic rebar without any additional bars, and it has the advantage of strip averaging the results to do the design, and the design will be done for the main reinforcement if appropriate using some strip averaged results, whereas the design for the basic panel reinforcement is done on a point-by-point basis. So where you have stress concentration, strips can be useful in a similar way to the peaks work, except peak zones provide reinforcement in two directions instead of just one direction. So a strip is a special situation of a peak, except it only works in one direction. Now, the reason why we're saying that is effectively, yes, the strip originally would have been only concerned with the side of the slab in which you asked it to provide the additional reinforcement. So you can see, as Patrick's highlighting here now, this strip is saying that it's bottom orientated, but we're not actually providing any additional bars on the bottom. So therefore that actually doesn't matter with regards to the side. Now, if you come down to the bottom of the screen there at the moment, Patrick, there is actually another new feature.
I've given you control there, Martin, so maybe
you've given me control. Okay.
Try and check that. Yep.
Yeah, perfect. So we have a new feature here whereby you can see, and Patrick showed this, both the moment, the axial force and the shear force, whereas previously that only showed you the moment. What we're seeing here, obviously, we can see the value of moment now changes in terms of its sign from tension on the top of the slab to tension on the bottom of the slab as it comes away from the supporting to the planted column, as you would expect. The shear check will travel all the way along this strip and in accordance with the offsets that have been specified. So that's the moment. So when we're looking at the shear, it will obviously, in accordance with the offsets, start, and it will then change side of the slab. So it will determine which point along this whole strip, albeit the IStructE document tells us to sample the reinforcement simply at a 1D section away from the supported column. But we're going beyond that, and we are doing that, but we are checking all the points along the strip averaged over the 4D width, because it's quite possible that you could have a lesser value of shear force as you perhaps move away to an area where you have tension on the bottom of the slab with a lesser amount of reinforcement. So you'd have a lesser value of shear force, but also a lesser capacity. So that's all being covered in that linear strip shear checking that's being done as part of that. And obviously, whatever the most critical point will be identified in this, and it will also tell you what side of the slabs. That's telling you that's the top reinforcement that is actually being identified there in that case as for what is being used for the critical design section. Some of these questions may require a more detailed follow-up. Some of them I would recommend are forwarded on to the support desk because they're maybe just a bit too detailed for the webinar and will require a little bit more unpacking with regards to, we have some questions with regards to, and Patrick referenced it at the beginning, with regards to staged construction, and the IStructE manual guidance on the design of transfer slabs does reference construction stage analysis and potentially how that's something that one needs to consider for designing transfer slabs, because the assumption with one whole model is that everything is built and as if at one time and then loaded at one time, whereas in reality the building is built in stages whereby you've got your level built and then it is subject to its construction stage loading and slab self-weight, and then the level above is cast on top of that. So you've got some locked-in stresses that happen as part of the construction process, and that can make a significant difference to the forces at play. The construction stage analysis is something that we have on our roadmap, and it's definitely something we'll be looking at in the near future. Our general recommendation for now would be that if you are concerned that the construction staging in your transfer slab is going to be something that you feel is significant, then modelling the slab as a standalone slab with its columns above and below modelled, and then just simply applying the loads from the levels above from a separate model. So you could do a separate model of all the levels above, get their support reactions and apply those as loads to the tops of the columns in the individual model that you have for your transfer slab, and that's a more realistic assessment of how the force will travel into the slab in a construction staging type of procedure. But there may be many situations where those concerns won't be as prevalent or prominent as others. So that would be what we would advise in the interim. But we'll be having more on the construction staging analysis in the near future. Okay, just another quick question. I'm not sure if this is actually covered. I'm just going to take the mouse back and go to the punching shear, and the manual adjustments that were made on these perimeters are obviously something that's part of the guidance with regards to when the spacing between the planted and supported columns, the clear spacing is less than 4D, then without adjustment the perimeters would overlap and potentially wouldn't pick up the forces at the critical points in between. So this is why the recommendation to reduce the perimeters was presented in this guidance. Indeed, we feel it's a very sensible and practical approach to that situation, and you can see obviously you're getting very comparable results between the two in terms of their peak shear stress. One of the things to keep your eye on though is the maximum averaging width does change when your perimeter widths change, in that it should be limited to a maximum of the actual clear spacing. So this is the effective depth averaging multiple in this case, because the columns are spaced at 3D in terms of support face to support face, then that has been entered as a reduced value from the 4 value that has been entered in the software. So just to bear that in mind. Okay, another question then with regards to planted and supporting column are closer than 1.5D, then we're obviously away from this type of analysis, and the IStructE document on the design of transfer slabs recommends that a strut and tie approach would be more appropriate, as that changes from being a B region, a Berners beam region, to something that is more of a discontinuous region where a strut and tie approach would be more appropriate. That's not something that we do, obviously, because this is a finite element analysis, which assumes that everything is operating as a B region in bending. So that would be something that we would have to carry out separately, where you feel a strut and tie approach is more appropriate when the clear spacing between the columns is less than 1.5D, which effectively means these values would never be less than, individual shear perimeter multiples would never be less than 0.75D would be the limit then of that lower spacing before the strut and tie would start to take precedence of the design approach. Okay, just having another quick scan of the questions. Okay, again, quite a lot of questions there, some of which possibly would be better handled post-webinar, and anything that has not been answered, we will endeavour to do our best to answer those in the follow-up document that usually is issued once the webinar is posted and goes live. All attendees would be given out a list of the questions that we feel would be beneficial for the wider sort of community to have answers on. So we'll do that as per usual. So Patrick, I'll hand back to you.
Okay.
And let you wrap things up.
Thank you. No, there's nothing more else I would like to add in regards to this topic, but what I would like to remind you again is how to get access to the software. Let me just check. I'm going to take this away. Okay. Pull open the, let me see. Yes. Just to recap what we covered today. So I worked pretty much mostly within MasterFrame and the Finite Elements module within that. You do get the Finite Elements module with the PowerPad suite. It is limited to one surface for 200 meter squared surface, and then your MasterFrame, that would also be limited to either 200 or 500 members on the subscription, depending on what you go with. With the Building Design Suite, you have unlimited MasterFrame members and unlimited FE surfaces, as well as unlimited surface sizes. So if you're dealing with large scale buildings or unlimited MasterFrame frames, the Building Design Suite is recommended. Or if it's just single surfaces, the FE elements should cover those as well. But with the PowerPad suite, you have the option to upgrade your concrete slab and wall design as well with that. So you can upgrade to unlimited FE surfaces and concrete slab and wall design within the PowerPad. And with the Building Design Suite, you go with the core package plus the concrete design upgrade as well, which would include your beams, columns, pads, and pile cap design as well, everything concrete related. So just how you can get access to that. These are the subscription options. Our licensing terms we are very flexible, so you can go as little as a quarterly subscription. You can save 25% by going annual on your subscription, or else you can make a one-off payment and go perpetual and have those for in perpetuity to keep. So there's no restrictions on how many engineers can use the software. You can have 100 engineers and 5 seats and share those 5 seats amongst each other on a first come, first served basis. And you can add users as much as you like. So there's no assigned users for that. If you do have any inquiries about those, if you want to try them, if you're an existing user and you want to take out a trial, or if you're a non-user and you want to get a trial of the software, you can go to your website, download a trial, and get access from there. And do feel free to give me a call direct for any inquiries, whether it's sales or technical inquiries about the software. I'd be happy to speak to you. So, yep, thanks everybody for tuning in today. We will post up links to all the relevant sources as well. You should be able to find, like, the IStructE guidance is available as free from their website. So definitely get your hands on that. And then, yep, the manual was the other resource that I used, as well as the Concrete Center publication on finite elements for designing concrete. So hopefully I've covered everything there. As I say, if you do want to get in touch, you can call up the number there or drop us an email, and we can take it from there. Okay, thank you everybody.
Okay, yeah, thank you, Patrick. Thank you for the insightful presentation. Okay, so ladies and gentlemen, thank you once again for joining us today. We hope you enjoyed the webinar and found it helpful. If you have any further questions or need more information, please do not hesitate to reach out to us. Our contact details are displayed on the screen. If you are interested in trying out the software, simply visit the MasterSeries website and submit a request for a trial. So have a good day, and we look forward to meeting you at our upcoming webinars. Goodbye.